Welcome to this talk on multi-arm bandits with bounded arm memory. I'm Arnab Maiti from Indian Institute of Technology, Kharagpur. My co-authors are Vishakha Patil and Arindam Khan from Indian Institute of Science, Bangalore. So we'll be dealing with multi-arm bandits, especially stochastic multi-arm bandits. So the stochastic multi-arm bandit problem is a classical framework used to capture decision making in uncertain environments. In this model, a decision maker is faced with some choices, and we call these choices as arms, and they have to choose one of the arms. Based on the arm which is being pulled, the decision maker gets a reward from an reward distribution which is unknown to the decision maker. So usually the decision maker is given a choice to either explore a new option or exploit the current options. So this can be better seen with this example here, where you have an usual restaurant which you visit and a grand opening. So based on your choice, you will get some kind of reward. So in this paper, we look at the streaming model. So in streaming model, arms arrive one by one in a particular order. Note that we don't assume anything on the order of in which the arms can arrive. That is, the arms can arrive in an adversarial fashion. So the algorithm can store the arms in the ARM memory. So here we have an ARM memory of size 2. So it means that the algorithm can store at most 2 arms in the ARM memory. So say the algorithm brings the first arm and then the second arm. Now the significance of the ARM memory is that algorithms can only sample those arms which are part of the ARM memory. Next, the algorithm can discard this particular arm 2 and then bring on the next arm, which is the arm 3. Now, in this paper, we look at the single pass algorithms. So, in single pass algorithms, you can discard one arm from the memory, but you cannot bring that same arm back to the memory in future. So, say you are discarding arm 2 from the arm memory, but you cannot bring it back into the ARM memory in future. So it's gone forever. So we cannot sample ARM2 from now on. So this model has a lot of applications. So one of the application is a job interview. So in a job interview, you have a company and some set of candidates, and you want to choose the best candidate among them. So usually the companies conduct multiple rounds of interviews, and it can be tiresome for the candidates. So the same objective of selecting the best candidate can be achieved by just conducting one round of interview. So here you have these 5 candidates, and the lady above will be questioning them. So the best candidate among them is denoted by a star above that candidate. So say first, the lady interviews the first 2 candidates, and say the left candidate is a better candidate, so we retain that candidate. Next, the next candidate comes, and the lady asks the questions to the next candidate, and she finds out that the previous candidate was better, so she retains the previous candidate. Next, a new candidate comes, and the lady asks some questions to the new candidate and finds out that the new candidate is a better candidate. Hence, it retains the new candidate and discards the old candidate. Next, another candidate comes, and the lady asks the question, and she finds out that the previous candidate was better. Hence, it retains the previous candidate and discards the new candidate. At the end, only one candidate is left, and we can declare this particular candidate as the best candidate. So in this paper, we looked at the stochastic multi-arm bandits from the perspective of regret minimization and best arm identification. So in regret minimization, we are given a stochastic multi-arm bandit instance with some expected rewards. So the arm 1 has reward mu1, arm 2 has reward mu2, and so on. And we denote the maximum mean as mu star. So the arm which has the highest mean is basically called the best arm, and its mean is mu star. Now say the algorithm will be sampling in each time step. So the mean of the arm, which is sampled in time step t, we denote it by mu I t. Now, expected cumulative regret is nothing but mu star t minus summation of expected means of arms which are sampled in each round or each time step. So, our aim is to minimize this expected cumulative regret. The second objective which we'll be looking at is best term identification. So here we want to find something called epsilon best term. So epsilon best term is an arm which has mean at least mu star minus epsilon, which is nothing but they are at most epsilon far from the best term. So what we want to do is find an epsilon best term with probability at least 1 minus delta such that number of arm pulls is minimized. So first let's go through our key results and discuss why it's important. So the first result which we have is with respect to regret minimization. So here we show that for any single pass algorithm, the regret which it will incur is n to the power 1 by 3 times t to the power 2 by 3 by m to the power 7 by 3. So this regret will be incurred whenever the number of arms n is more than the arm memory m, and this lower bound will even hold for random order arrival. So random order arrival is nothing but you have the set of all possible orders in which an arms can come. So you choose one of the orders uniformly at random. The second result which we have is with respect to best term identification, where we find an epsilon delta pack algorithm with order R arm memory, which has an optimal R round sample complexity. So optimal R round sample complexity is nothing but this particular expression. So why it's important? Because this immediately leads to the following corollary. So we have an epsilon delta pack algorithm, which is nothing but finding epsilon best term with a probability 1 minus delta. So we have this epsilon delta pack algorithm with order log star n arm memory, and we obtain the optimal worst case sample complexity. So let's go through the intuition behind this the proofs which we have. So first let's go through the intuition behind the lower bound of regret minimization. So here we are given some input instances. So for example, we consider 3 input instances, and one of them will be sent to the algorithm, but the algorithm doesn't know which input instance has been sent to it. So in each input instance, you have some arms, and below the arms, we have specified the means of the arms. In each input instance, you can see some means have been highlighted with red color. So those arms are nothing but the best arm. And we consider the arm memory size to be 2. So say someone designed an algorithm where the first arm is being pulled for very less number of times. So in that case, for input instance 1, the algorithm has a good chance to discard the best arm, and it can keep on sampling suboptimal arms and incur huge regret. Similarly, if someone designs an algorithm where the second arm is pulled for less number of times, then in input instance 2, there is a good chance that the algorithm can discard the best arm and keep on sampling suboptimal arms. Now suppose someone designs an algorithm where the first 2 arms are sampled for more number of times. Then in input instance 3, you will incur huge regret as the arms sampled are suboptimal. So what do? We try to balance these 3 regrets which we get for each input instance, and we do it by appropriately choosing the epsilon parameter and using KL divergence and some information theory properties. We finally get the lower bound of t to the power 2 by 3. Next, let us look at the best term identification algorithm. So we'll explain you one of the subroutines here. So say you in our subroutine we have some levels. Say we have 5 levels here. This is just one example. So in each level you store an arm. You store a value between 0 and 1 which corresponds to the empirical mean of the arm which is being stored there, and you store a counter. So the counter kind of signifies how many arms have reached that level before we again initialize the counter back to 0. So initially everything is initialized to 0 here in each level. So say at one particular moment of time, this is the configuration, and an arm comes into the first level. So we sample the arm for S1 times, and we observe that the empirical mean is 0.58. So we discard this arm. Similarly, another arm comes and we repeat the same process, and we observe that its empirical mean is 0.70. Then we discard the arm stored in level 1, and we bring the current arm into the level 1 along with, and we store the empirical mean too. And note that once we store this empirical mean, we don't again resample this arm in this particular level, and we increase the counter from 10 to 11. Suppose we keep on doing this thing and the counter reaches a constant C1. Then we promote this arm to the next level and initialize the constants back to the counter and the stored mean back to 0. And then we repeat a similar procedure for level 2, like sample it for S2 times. Then we get an empirical mean which is greater. Then we replace this with the new arm, and then we increase the counter. And similarly, if we keep on doing this, we'll hit a constant C2, and then we'll promote it to the next level. Now, if we keep on doing this, at the end, we'll be left with one particular arm in the highest level, and we can declare it to be the best arm. And we showed it using concentration bounds that we will be finding an epsilon best arm with a very high probability. So let's summarize the results. So using KL divergence and information theoretic proof, we showed that any single pass algorithm will incur a regret of say t to the power 2 by 3 when the ARM memory size m is less than n, and this will even hold for random order arrival. If the ARM memory size was same as n, then you had the standard UCB algorithm which achieves a upper bound of square root t. So you have a dichotomy here, and we also have a matching algorithm for this t to the power 2 by 3 up to logarithmic factor, and that is nothing but uniform exploration. So you basically sample some arms initially, and then you choose the best arm among them and keep on pulling that arm in future. Now you look and our second result was epsilon delta pack algorithm, where we showed a level based algorithm, and we'll achieve this particular expression which is nothing but optimal R round sample complexity. So some open problems in this area are: can we obtain instance dependent lower bound and upper bound on the expected cumulative regret for single pass multi-arm bandits algorithm, provided we have bounded arm memory? The second thing is that for multi-pass multi-arm bandits algorithm, can you obtain lower bounds and upper bounds similar to what we achieved for single pass algorithm? Last, observe that we have a log star n algorithm which achieves the optimal worst case sample complexity. So can you find order 1 arm memory based algorithm which will obtain an optimal worst case sample complexity? So thank you. And if you are interested, please have a look at our paper, which is multi-arm bandits with bounded arm memory, near optimal guarantees for best arm identification and regret minimization.